We're going to keep talking about probability, and today we're going to include the word or. Before we go on to our new formula for today, I wanted to make sure we were comfortable reading charts. So here's a chart from Statista that says Nike cuts out the middleman. It's direct-to-consumer sales as a percentage of Nike's total brand revenue. I want you to look at 2015, which is right here, and we can see that it's somewhere between 20% and 25% of their sales. What I want is for you to be able to read the chart and see that it's really closer to the 25 than it was for the 20, so a good estimate would be like 23%. If I look at 2019, I can pick out that here's 30, here's 35, and this time it looks like it's closer to the 30 than to the 35, so maybe I'm going to call that like 31% or 32%. Know that if you were in my class, I would have a little bit of built in there for your answer that I'm not expecting everybody to get 23%, maybe you get 22.5. I'm happy with that. You might tell me 31 or 32, and those both seem like good answers. At the spinner, I have numbers 1 through 6, and I said let's find the probability of spinning the spinner one time and getting either a red or an odd. So what I'm going to do is go to the spinner, and I'm going to circle all of the odd ones, which was 1, 3, and 5. When I look at the odd ones being circled, I can see 1 was on red, and that's already odd, so it's already be counted. I don't have to do anything new for that. So I would count that there are 3 ways to get a red or an odd over the 6 total outcomes. I'm going to reduce that to 1/2. Great. In our next example, let's find the probability of getting green or an even number. So green or even. If I start with even, I can see 2, 4, and 6 are even, but I haven't circled the green one yet, so let's go ahead and put the green one in there too, which is the number 3. Now I have 4 out of the 6 choices. We're going to reduce that to 2 over 3. There's a little difference between the first case and the second case, and the big difference here is something called mutually exclusive events. When 2 events cannot occur at the same time, we call them mutually exclusive. So what was mutually exclusive here? Green and even. I can see I had an odd on the green, so those 2 things didn't happen at the same time, versus if I go back where we talked about looking at landing on a red or an odd, they both happened at the same time. So we just have to pay attention to, is there something they have in common? Is there something that they don't? When things have something in common, it's not mutually exclusive, but if things cannot occur at the same time, we call that mutually exclusive. In this example, we have a survey of 400 people asked to pick their favorite sport. Their responses are in the chart below. Find the probability of a person's favorite sport is basketball or baseball. We can see basketball, 87 picked that to be their favorite. Baseball, that was 45, and remember there was a total of 400 people. 87 and 45 gives us a total of 132 over 400. Anytime you have a fraction, you want to make sure you reduce it to lowest terms. So I can see 132 and 400. I could divide by 4. I end up with 33 over 100. Let's stick with this chart and find the probability a person's favorite sport is not football. Okay. So you have 2 choices here. You can add up 63, 87, 45, and 37. That'll tell me how many people pick soccer, basketball, baseball, or hockey. Or I can say we had 400 people, 168 of them said football was their favorite, so the rest didn't pick football as their favorite, so that says there's 232 people that didn't pick football. 232 over 400. Again, we want to make sure we reduce that to lowest terms. This gives me 29 over 50. So let's include our formula. When we learned set theory, we had a formula for cardinality that said the number of elements in the union of A and B is equal to the number of elements in A plus the number of elements in B minus the number of elements in the intersection. We're going to use the same type of formula, but just switch it to probability. So the probability of A or B will be the probability of A plus the probability of B minus the probability of A and B. These formulas are both accomplishing the same task. We're just taking out counting any occurrence from happening twice. A survey of 50 people asked which streaming service a person had used in the previous week. 38 watch Netflix, 24 watch YouTube, 19 watch both. What's the probability a person selected at random had watched Netflix or YouTube? I'm going to call Netflix N. I'm going to call YouTube Y. Using our formula, we would have the probability of N or Y will be the probability of N plus the probability of Y minus the probability of both, which is N and Y. So in Netflix, we had 38 of the 50 people. For YouTube, we had 24 of the 50 people. And then both, we had 19 of the 50 people. So even though we could have reduced the 38 over 50 and the 24 over 50, I'm not going to. I want to leave them the same. That way it's easy to figure out our answer. That way I have a common denominator. So I look at 38 plus 24 minus 19 gives me a total of 43 over 50. Let's do a little probability with Senate. So this is Senate from 2019. This is not current because we just had an election and things are changing. So 2019 numbers said that there were 53 Republicans, 9 were women, 45 Democrats, 17 were women, and 2 independents. If a senator is selected at random, let's find the probability that the person's a woman. Important, we have 100 senators. So I have 9 women and 17 women. So 9 and 17 gives 26 over 100. Let's do this one as percentages because we haven't done that yet. So I say that's 0.26, which is 26%. Okay, same thing. Let's look at probability of selecting a Republican. There were 53 out of the 100 total, which gives me 0.53 or 53%. A Democrat or a woman. Well, we have a couple ways to do this. We could start by saying, well, we know there's 45 Democrats, which included 17 women, but there's 9 more women that we can grab from the Republicans. Out of the 100 total senators, 45 plus 9 gives 54 over 100, 0.54, which is 54%. And then not a Democrat. So not a Democrat means you're either a Republican, 53, or an independent, which is 2, over the 100. So this is 55 over 100, 0.55, which is 55%. Let's just say part C, it did have the word or in there, and we could have done it a long way where we could have said, let's look at Democrat, let's look at women, and then we could subtract what was both. So I like that you have choices. That way you do whatever makes sense to you, right? Whatever comes to your head is how you should do it. So if you thought, you know what, I want to do it this way with the formula, you would say Democrat is 45 over 100. Women, we said earlier, was 26 over 100. And what you would have to subtract would be the 17 over 100, which was both. I still get 45, 26, and 17 is 54. So it's really just a matter of choice of you if you like the formula or if you can see the answer without it. Let's pick a different chart. This one has a survey of 250 students reported whether the students went to school full-time or part-time and whether or not they had a job. So in the chart, we're going to look for what's the probability that the student was full-time. So when I'm looking at full-time, I want to go all the way across to the 91 over 250. Now let's look at working full-time. So working full-time, I want to look down and it says 59 over 250. Let's go ahead and make those percentages so we get a better feel for those numbers. So 91 divided by 250, this is 36.4%. And then 59 divided by 250, this is 23.6%. We're going to stay with this chart and look at some more probabilities. So the first one says probability full-time and work full-time. So go to school full-time and work full-time. So we're putting the column and the row together. Full-time student, full-time work. I can see there were 14 people out of the 250. And then full-time student or work full-time. Again, we have these choices where I could go across and say Full-time student was 91 over 250. Full-time working was 59 over 250. And then both was 14 over 250. The 91 plus 59 minus 14 gives me 136, and that was over 250. Again, let's just change both of these back to percentages. So 14 over 250, this is 5.6%. And then 136 divided by 250, this is 54.4%. Okay. The next chart has only percentages and not numbers. So I have a race, a 5K, a 10K, and a 15K, and then I broke it into two categories, 18 to 25 and 26 to 40. In this particular chart, somebody can't run more than one race, so they had to pick one. Say maybe they all started at the same time. The first probability we're going to look at is what's the probability that a person, if I selected a runner at random, would be 18 to 25. So I'm going to read all the way across, and I can see it's 0.60. Same thing, I want to look at the probability that someone ran the 5K. I look all the way down, and it says 0.55. Now I want to get the probability that someone was 18 to 25 or they ran the 5K. So we said 18 to 25 was 0.60. We said 5K was 0.55. What we need to do now is subtract the both. So 18 to 25 and 5K, which was 0.33. So 0.6 plus 0.55 minus 0.33 says 0.82. Staying with this chart, let's do a couple more. First one says probability of 26 to 40 or 15K. 26 to 40, that was 40%. 15K was 20%, but then 26 to 40 and 15K was minus 0.10. 40 plus 20 minus 10, that's 50%. How about 5K or 15K? So the 5K was 0.55. The 15K was 0.20. This time I have no intersection because we said everybody's got to pick one race and you're only going to run one. So my total is 0.75. We're going to do a few problems about cards. So here's a little visual so you can see what we have. 52 cards, we have 4 suits, 13 cards in each suit. Let's start by saying we're going to pick one card at random, and what's the probability of getting an ace? Well, I can see I have 4 aces. Out of my 52 cards, you can reduce that to 1 over 13. B says let's not get a king, right? So the first one I said I want to get an ace, and the second one I say I don't want to get a king. Well, there are 52 cards altogether. 4 of them are kings. 52 minus 4 is 48 cards that are not kings. 48 over 52 gives us 12 over 13. What about if we want to pick a diamond? Well, we have 13 diamonds out of our 52 cards, which gives us 1 over 4. But we always think we have 13 of each suit. So if I have 13 diamonds, I also have 13 clubs. And in part B, I want to find the probability of not getting a club. So we're going to take our 52 cards and we're going to take all the clubs away, which will leave us with 39 cards left. So our 39 out of our 52, which becomes 3/4 of the cards, are not clubs. How about if I pick a card and I want to know what's the probability it's a face card or a club? Well, face cards mean there's a face on it, so I have 3 of each suit. So 3, 6, 9, 12. I have 12 face cards. I have 13 clubs. But I also have to think about, well, how many are both? So if you look over here, you can see for the clubs, I have 3 of them that are face cards and clubs, so I want to subtract those. I get 12 plus 13 minus 3 is 22 over 52. Kind of ran out of room, so I'm going to write up here that this was 11 over 26. And the last one says, what if I had an ace or a 10? Well, there are 4 aces out of the 52. There are also 4 10s out of 52. This time, an ace can't be a 10, so I don't have anything to subtract. I have 8 over 52, which is 2 over 13.